In this class, we are going to consider two examples of time-dependent perturbation theory. Initially, we consider the case of a constant perturbation and we apply this time-dependent perturbation theory to see how or what is the probability of making some transition from some initial state to the final state. And then later we consider a harmonic perturbation case, and again we will analyze it for finding the expression for the probability density to make some transitions. So here in this particular problem, we consider the case of a constant perturbation acting on the system. So that is given by this particular expression W prime of t, which it is equal to 0 for the time t less than 0, and it is equal to W for time t greater than 0. So still it's a time dependent perturbation because it varies with time, but for time greater than 0 it remains constant, the perturbation remains constant. Now the probability for the system to make transition from an initial state psi I to some final state psi f is given by, we have seen an expression in the last class, so we take it as PIF of t is equal to 1 by I h cross square. Then we have integral 0 to t e raised to I omega fit dt prime. Then what we had is the matrix element psi f w prime psi I, and we have to consider the modulus square of this quantity. So this is the expression that we have seen in the previous class. Now for this particular problem, this w prime is given by this constant perturbation, so you can take it outside the integral. So this can be written as 1 by h cross square. Then if you take it outside, this is psi f, then w prime is constant and its value is given by w for time greater than 0. So let's write it as w psi I square. Then we have integral 0 to t e raised to I omega fit prime dt prime, the modulus square, where this omega fi, if you remember, this omega fi is given by ef minus ei by h cross. So what you get from here is this is equal to 1 by h cross square. So let me write it as this entire thing can be written as the matrix element wfi. So the modulus of wfi square, then the integral will give us e raised to I omega fi t prime by I omega fi. Then you have to apply the limit from 0 to t, then you have to take the modulus square. So this will give us wfi by, so modulus wfi square by h cross square, then you have omega fi coming from here, omega fi square. So when you take the modulus square, this will give us 1 and omega fi square. Then when you apply the limit to the integral, this will give us e raised to I omega fit minus 1, then the modulus square. Now you can prove that this quantity, this can be done as an assignment, this quantity will give us this entire quantity modulus square will give us 4 sine square omega fi t by 2, and when we substitute it here, so this is the expression for the probability density. So this can be written as, this is equal to wfi by h cross square, wfi square by h cross square. Now you can rearrange these terms as sine omega fi t by 2 divided by omega fi by 2 whole square. If you rearrange, then we put this quantity sine square, all this quantity we take or we define it as some function f of t and omega of I, omega fi. So the expression for the probability density will become wfi modulus square divided by h cross square into f of t omega fi, where f of t is given by this expression, sine square omega fi by 2t divided by omega fi by 2 the whole square. Okay, so you can see that the probability depends not only the matrix elements omega fi, the square of the matrix elements, but it also depends some function which is a function of time and the frequency omega fi. So if you plot this function f of t omega fi as a function of omega fi, you will get a plot like this. So now let's see what are the observations that, or what are the inferences that you can get from this graph. Let's write it one by one, the observations. The first one is that this omega, this f of t omega fi, it exhibits a peak at omega fi is equal to 0. You can see that it has a peak at omega fi is equal to 0. That means when this ef minus ei by h cross is equal to 0. So what does it tell? The probability is maximum when the energy of the final state is same as the energy of the initial state. So it tells you that the constant perturbation neither transforms energy to the system nor removes energy from it. There is no energy change in the system. Okay, so that is the first thing that we observe from this plot. Now the second thing is that the first zero of this function occurs when this omega fi t by 2 is equal to pi, because we have a sine function. So you can see that the first zero occurs when this omega fi t by 2 is equal to pi because of the sign dependency. So it tells you that the first zero occurs when this omega fi is equal to 2 pi by t, right? You can see that on either sides of this zero, the function becomes 0 when this omega fi becomes 2 pi by t. So we can calculate the width of the transition. The width of the transition is given by this width, and this is given by 4 pi by t. The width of the transition is given by 4 pi by t. So you can write the delta omega, the width of the transition is 4 pi by t. If you multiply with h cross, you can write it as h cross delta omega, which is delta e, is given by h cross into 4 pi by t. If we take the time as delta t, the time interval during which the perturbation has been turned on, so we take this as delta t, the time interval of perturbation acting on the system, then you can write this delta t means delta E delta t, which is approximately of the order of h cross on the right hand side. So this is in accordance with the uncertainty principle. Now delta E is the mean energy change involved in a transition with appreciable probability. So if delta T is small, we will have a broader peak, because if this T is small, or when delta T is small, we will have a broader peak, and as a result what we have is, so when delta T is small, this delta E can be very large. The uncertainty in the energy can be very large. So we can tolerate a fair amount of energy non-conservation for this transition. So that means if a transition, or if the perturbation is acting for a very very short time period, then you don't need to worry much about the energy conservation. But if the perturbation has been on for a very long time, then you can see that this delta E will be very small. If delta T, or the perturbation, is on for a long time, then delta E will be very small. Then we will be having a very narrow peak, and approximate energy conservation is required for a transition to happen. Okay, so the energy conservation basically depends on the time scale on which this perturbation is actually happening. If it is a very small short duration perturbation, then conservation is not that much important. But if it is acting for an appreciable long duration, then the conservation has to be considered, energy conservation has to be considered. Now the third point that you can observe is that in the limit t goes to infinity, this f of t omega fi is given by 2 pi h cross t delta of ef minus ei. So this actually stems from the definition of the Dirac delta function. So don't worry about how to get it. Then what is the implication of this thing? In that case, the probability for making a transition from I to F is given by W Fi modulus square divided by H cross square. Then you have 2 pi H cross T delta Ef minus Ei. So this is equal to 2 pi by H cross T WFI the modulus square delta EF minus EI. That is, as time t goes to infinity, you can see that this probability also goes to infinity, right? Which is unphysical usually. The maximum probability cannot be greater than 1. So to make it a physically acceptable thing, we conclude that the first order perturbation theory is valid only for time such that this t is far less than h cross by w f I square. So this is the validity condition for the for the time dependent perturbation theory, because in this limit your t is limited by h cross by this quantity, and you will be having a finite probability. When this is very less, you will have a finite probability. Otherwise we will end up with an unphysical situation where the probability indefinitely increases. Okay, so this validity condition has to be considered. So now we consider the harmonic perturbation case. So we consider a system such as an atom or molecule exposed to harmonic perturbation. Harmonic perturbation means an atom or system exposed to an electromagnetic radiation, for example. So for convenience, we shall assume that the states involved are the discrete states. So a harmonic perturbation with an angular frequency omega has the form W prime of t is equal to 2W0 cos omega t. So this 2 actually has been introduced for some simplicity. So this is can be written as W0 e raised to I omega t plus e raised to minus I omega t. So this is the form of the harmonic perturbation that we are going to consider. Then the matrix element WFI prime is given by psi f WF prime psi I into, so this is, now for simplicity what you can write is, instead of this WF you can simply write instead of this psi f you can simply write f, the final state. Then you can write instead of W0, instead of W prime we have W0, then the initial state f, then we have e raised to I omega t plus e raised to minus I omega t. If we substitute for this in the expression for Cm1 of t that we have seen in the previous class, or Cf1 of t, Cf1 of t is given by 1 by I h cross integral 0 to t f W0 I e raised to I omega t plus e raised to minus I omega, let's say t prime. Then we have an e raised to I omega fi t prime dt prime. So this is equal to, let's say, W0 fi, the matrix elements, because this W0 is constant or independent of time. The time dependent part is given by this exponential terms, so that you can take outside. So this divided by I h cross, then integral 0 to t, can write e raised to I omega fi plus omega into t prime plus e raised to I omega fi minus omega into t prime, all multiplied by dt prime. So now if you integrate these things, these are very straightforward integral that you can do yourself. So if you do that, what you get is, you get an expression for Cf1 of t is equal to W0 fi. Then what you get is, you get 1 minus this integral, and simplification you have to do yourself, 1 minus e raised to I e fi plus h cross omega into t by h cross divided by EFI plus h cross omega plus 1 minus e raised to I EFI. So this EFI minus h cross omega into T by h cross divided by EFI minus h cross omega. So this is what you get if you do that integration and if you rearrange the terms. Now for T, you can see that for T going to infinity, in the limit, this CF1 modulus square, this will become finite only if the denominators goes to 0. That means only if EFI plus h cross omega goes to 0 or EFI minus h cross omega goes to 0. So in this particular limit, when time goes to infinity, you will have a finite value for this probability amplitude terms CF1 only if the denominators are going to 0. So this condition tells you that EFI is basically EF minus EI plus h cross omega is equal to 0, or that means your EF is equal to EI minus h cross omega. So what basically it tells you that your final state energy is less than your initial state energy by 1 unit of h cross omega. So it transfers a quantum of energy to the system, right? So there is a energy transfer to the system. Or if you consider this condition has to be satisfied, then you can write that EF minus EI minus h cross omega is equal to 0, which tells you that your final state EF is equal to EI plus h cross omega. So this, it tells you that the system receives a quantum of energy. So the final energy state is greater than the initial energy state. So what we have basically here is we have two processes. This is an absorption process, and this first term, this is an emission process. So either the system can release some energy or the system receives some energy. So accordingly, there are two possibilities. When the system is subjected to a harmonic perturbation, it can have an absorption or an emission process. So the effect of harmonic perturbation with an angular frequency omega is to receive from the system or to transfer the system a quantum of energy h cross omega. That is, the system either absorbs or emits energy. Since emission is happening in the presence of electromagnetic radiation, this emission is usually referred as the stimulated emission process. At a given time, either absorption or emission happens. These two processes will not happen together. Either of these two processes can happen at a given time. So let's consider the absorption case. So if you consider the absorption case from this expression, we need to retain only the second term. We need to consider only the second part, because these two things cannot happen simultaneously. So let's consider the absorption process happening in the system. So in the absorption process, our expression for CF1 of T becomes W0 Fi. Then what you can write is 1 minus e raised to I E Fi minus h cross omega into T by h cross all divided by E Fi minus h cross omega. So this refers the absorption process. So this can be simplified like W0 Fi by EFI minus h cross omega. Then if you take e raised to I EFI minus h cross omega into t divided by 2h cross, and then the remaining terms can be written as e raised to minus I, then EFI minus h cross omega into t by 2h cross minus e raised to I EFI minus h cross omega into t divided by 2h cross. So this can be simplified. If you simplify it, this can be written as minus 2I omega 0 Fi divided by EFI minus h cross omega e raised to I EFI minus h cross omega into t by 2h cross. Then you will get a sine term, sine EFI minus h cross omega by 2h cross into t. So if you assume that your system is initially in the state I, at time t is equal to 0, then the probability for this system to find it in a state f at a later time t is given by the modulus square of CF1 of t, right? So that means the probability for the system to make a transition from our initial state to the final state is given by 4 times W0 Fi modulus square. Then what you have is sine square EFI minus h cross omega by 2h cross into t divided by EFI minus h cross omega whole square. So if you take this 4 from here to this quantity, this will become EFI minus h cross omega by 2 whole square. Then these two terms will look similar. This one and this denominator term looks similar, and this is what we have seen as the function f of t EFI or omega Fi in the constant perturbation case. Okay, so now we plot this probability. If we plot the probability as a function of EFI minus h cross omega, what you observe is, so what you get is, you will get a plot like this, quite similar to a plot what we have seen in the case of constant perturbation theory. The difference is that we have plotted the probability here along the y-axis and EFI minus h cross omega the x-axis. So you can see that the transition probability actually oscillates sinusoidally as a function of time. You can see that the width of this transition is given by this difference, and this is given by 4 pi h cross by t, and the full width at half maximum of this peak is usually given by approximately, this is 2 pi h cross by t, and this height of this transition, so this is proportional to t square. The height is usually given by, this is given by W0 Fi, so this is the modulus square, t square by h cross square. So this height is proportional to square of time and the width is inversely proportional to t. Okay, so height of this is proportional to t square and width is proportional to 1 by t, and hence you can see that the area is proportional to t. So the perturbation theory is valid, as I mentioned in the previous case, when this probability is far less than 1. Okay, so as long as t is small enough such that this quantity EFI minus h cross omega by 2h cross into t is far less than 1. So as long as this condition is satisfied, we will be having a finite probability. So it tells you that EFI minus h cross omega is far less than 2h cross by t. So since the height is proportional to t square and the width is inversely proportional to time, we have seen that the area under the main curve is proportional to time t. So that means the probability of finding this system in state F is proportional to time t. So that means if you keep the perturbation on for a long duration, you can find you will get maximum probability or an increased probability of being found the system in some final state F. It is also clear from the plot that the probability of finding this system in a state whose energy differs considerably from the initial state En is smaller than the probability of finding it a neighboring energy state, right? Because it peaks, these peaks happen very close to this value for energy. So if you consider, if you consider the transition from one state to a faraway state, if you consider states like this, then the probability is very less. So that's what I told you, the probability of finding the system in states whose energy differs too much from the initial state is very less compared to the probability of finding it in the neighboring energy state. So in conclusion, the effect of harmonic perturbation is to transfer to the system or to receive from it a photon of energy h cross omega. In contrast, in constant perturbation case, we have seen that it neither transfers energy to the system nor removes energy from it. Okay, so that is the basic difference between these two perturbations. There is no energy transfer takes place in constant perturbation case, but in harmonic perturbation case, it can either transfer energy to the system or it removes energy from the system. Both the absorption and emission process are possible.